Hey everybody, it's Ripley back again. We're going to talk about a gentleman by the name of L'Hôpital, not La Hospital. I know you're going to say it, and it's going to be annoying, but it's L'Hôpital because he's a Frenchman. Ooh, I'm trying to erase that. It was a little smudgy. All right, I'm going to just put it out there. I'm going to give you the rule, and then we'll talk about what it really means. Okay, the rule simply says this. It says, suppose f and g are continuous and differentiable. I guess I should have just said diffable, right? Because that implies continuity. And g prime of x is not equal to 0 on an open interval, Okay? Now, also, this, I know it takes a long time to get L'Hôpital's rule out because it's so blah, but you'll see how useful and helpful and quick it is down the road. Also, limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals 0, or, now this is a huge or in here, okay? Limit as x approaches a of f of x equals positive or negative infinity. And, now these ends, so these two are linked together, and then we've got this or, and limit as x approaches a of g of x equals positive or negative infinity, right? Sorry, not cool, Ripley. All right, so this sets the whole stage. What we're saying is, if I've got two functions, and the limits both either go to 0 or positive or negative infinity, then this implies the limit as x approaches a of f of x over g of x, is equal to the limit as x approaches a of f primed of x over g primed of x. Now, your mind should be just a little blown by that one, and I'm gonna prove this guy to you. I'm gonna prove this little general case for you here in a sec. But I want to talk about something first. All right. Let me give you an example first, just to get your brain wrapped around what I'm talking about. If I take the limit as x approaches 0 of sine of x over x. Now, we already know that this is equal to 1, and there are geometric proofs, and there are god-awful numerical proofs that we can do, or we can simply use L'Hôpital's. But let me make sure that you understand something first, and I'm going to do, I'm going to change. I want you to know the indeterminate forms. Indeterminate forms. They are very simple. To be able to use L'Hôpital's, what all of this god-awful tongue twistery is telling us is that what we need to do when we plug it in, right? The first step of any limit is plug it in. What we're going to get is either 0 over 0 or in plus or minus infinity over plus or minus infinity. And what this says is that this can be positive infinity and this can be negative infinity as long as it's infinity over infinity. If it ain't these two forms, I can't use L'Hôpital's. There are other forms there are other indeterminate forms out there, mathematically speaking. But to be able to use L'Hôpital's, it's got to be in one of these two forms. So I stumble over here. Oh, look, 0 over 0. Yay, smiley face. It's a L'Hôpital indeterminate form. Now, I want to be really, really clear here because you're going to make silly errors if you're not careful. First things first, the way in which we denote that we're using L'Hôpital's, because our limit is going to change drastically by use of L'Hôpital's. So I got to make sure that the people looking at my work, or the people, more importantly, grading your work, know what the heck you're doing, right? So what this says is, by L'Hôpital's, I know I have the limit as x approaches 0 up. Now stop. What does this say to do? It says take the derivative of the top and take the derivative of the bottom. It does not say take the derivative of the quotient. If you make the error, that's the error that you're going to make. You're going to use quotient rule. Notice this is not quotient rule. Quotient rule. That's not what L'Hôpital claimed. Multiple exclamation points, because that's the error you're going to make. You're not using the quotient rule. You're taking the derivative of the top. What's the derivative of sine of x? cos x. What's the derivative of x? 1. Yay! Limit as x approaches 1 is, or excuse me, as x approaches 0 of cos x over 1 is 1. Yay! See how much easier that is? Such an easy proof. All right? Super simple. All right? We can also use L'Hopital's in a really kind of interesting way. I can take the limit. This is a little bit, you got to be really careful with this notation because I can actually take limits at infinity. I don't have to just take them at specific values of a. I can take, as long as I get one of these two indeterminate forms, I'm in good shape. I can take the limit as x approaches positive infinity of x squared over e to the x. Let's do that one. All right? Should be relatively obvious that this guy is equal to infinity over infinity. Yay! L'Hopital's. Okay, so I use my notation by L'Hopital's. This tells myself and people that are reading my work what I'm doing at this step right here. The derivative of the top, not quotient rule, the derivative of the top is 2x. The derivative of the bottom is e to the x. When I plug infinity in again, I get infinity over infinity. Yay! That means I get to use L'Hopital's again. As long as I'm ending up with indeterminate forms, I can continue to use L'Hopital's, right? So by L'Hopital's, I take the limit as x approaches, infinity, and what do I get? Derivative of the top is 2, derivative of the bottom is e to the x. What does that tell me? As x goes to infinity, this guy is 0. I know that this limit is 0, but it's far more helpful. It's far more useful than that. Granted, if you could take this limit using L'Hopital's, good for you. You know how to use L'Hopital's. But if you get a little more insightful, if you just drop just one little level below that, figure out what this limit really tells you. What this limit tells you is that exponential functions grow way faster than polynomial functions. Had I put x to the 100th here, x to the 100th grows really, really fast, right? But if I took enough derivatives, I would always get down to a constant over e to the x, wouldn't I? So therefore, that limit's always going to be 0, which means way back when we talked about asymptotic behavior, that tug of war that takes place at infinity, that tug of war that takes place at infinity is won by the exponential function. No matter how big and god-awful I want to make this polynomial function, e to the x will always win. Because you take enough derivatives, it goes down to a constant, and we get 0. So remember, L'Hopital's is a tool that we're using to understand limits, not just to take limits. Now, let me prove this guy for you, okay? It doesn't take very long. It's kind of cool. I'm going to just go whoop right here. Now, remember, what I'm going to do is I'm going to prove it for this case. Proving it for the infinite case, that takes a little bit more time. All right, I have to be a little more robust in my analysis. I'm not going to do that for you. But I am going to prove it in this general case because it's pretty simple and it goes super fast. Watch. If I take the limit as x approaches a of f prime of x over g prime of x. Well, I know that g prime of x and, I know that this guy, if I plug these in, is going to give me f prime of a over g prime of a, right? And I know by definition of derivative, this can be written as the limit as x approaches a of f of x minus f of a over x minus a over the limit as x approaches a of g of x minus g of a over x minus a. Now I want you to notice right here that I'm moving backwards. The reason I'm moving backwards is because I get more information that way. Think of it as proving an identity. Remember when we proved identities back in trig? We always wanted to start with a side. A general rule, not one that we adhere to all the time, but a general rule was start with the side that gives you the most information. Now it should be relatively obvious here that we get that this goes away and that this goes away, and that we also know, those are going to cancel algebraically. I also know that the limit of a quotient is the quotient of the limit, so I can actually rewrite this thing as the limit as x approaches a of f of x minus f of a over g of x minus g of a, right? We got that. It's a g of x. True? Remember, limit of quotient equals the limit. We got an algebraic cancellation. I know I'm rushing through this, but I know that proofs of theorems absolutely rivet you guys. But I also know that f of a and g of a are 0. So guess what I get? This is the limit as x approaches a of f of x over g of x. Right? We know that these guys are 0 because when I plug it in, I get 0. And I'm done. That is a QEDer. Yay for me. Okay, cool. That's the proof of that. Now, let's see. We're going to deal with other indeterminate forms here in just a second, but I'll meet you on the next page. I'm going to take a little break. Okay, everybody. We're going to talk about another couple of indeterminate forms and how, remember, to use L'Hopital's, I want to emphasize this. I've got to be in one of these forms, or I'm screwed. I can't do anything. Okay? I cannot use L'Hopital's. But there are other indeterminate forms, and you may say, well, Ripley, how? Well, okay, well, so I've got to mush any other indeterminate form into a form that looks like this. For example, if I do 0 times infinity, that is an indeterminate form. Okay? Excuse me. That's an indeterminate form. I don't know who wins this. Is 0 strong enough to beat infinity, right? Because 0 times anything is 0. Or is infinity, because it's infinity, especially when we're talking about limits, right? Because I never quite get to 0, and I never quite get to infinity. So who wins this tug of war? Well, there's an algebraic trick. Do you agree that I could rewrite 0 times infinity as 0 over 1 over infinity, right? Which turns into 0 over 0. I could also rewrite this as infinity over 1 over 0. Now, think limits, you guys. We're talking about limits. That's a really good way to deal with this. All right? Now, this turns into infinity over infinity. Both of these they definitely earn the smiley face stamp of L'Hopital's approval. All right. Now, this is the key. When you see this situation right here, when you got this and you know that you can convert it into one of these two, you know that you're on the right track. Now, I'm going to talk about 3 other indeterminate forms, and then I'm going to teach you how to get them here, and then once they're here, we can get them here. The 3 other indeterminate forms, so 3 other I'm going to be lazy here, forms. Okay, the first is 0 to the 0. And you can sort of look at this and be like, yeah, that kind of makes sense. Because who wins, right? Because anything raised to the 0 power is 1. And 0 to the anything is 0. So how do I get this into one of these forms? Or more importantly, let's see this as an indeterminate form. Well, the trick is the same. And there are 3 of these forms that I'm going to show you first. And then I'm going to show you the trick. And then you can apply that anytime that you see one of the next 3. The other one is infinity to the 0. Likewise, right? Who wins? Infinity raised to anything is infinity. But wait a sec, anything raised to the 0 is 1. So will I get 0? Will I get infinity? Will I get some number in between? Lastly is 1 to the infinity. Likewise, who wins? Especially in the limit context, right? We're talking about limits here. Who wins this? 1 to the anything is 1, and anything to the infinity is either going to be 0 or infinity, right? In the limit context. All right, I'm going to give you a problem that is going to help you get through this. I'm going to put it up here. All right? Now, I'm going to take the limit as x goes to 0 from the positive side of 1 plus sine of 4x. And I'm going to raise this thing to the, let's see, what do I want to raise this to? I'm going to raise this thing to the cotangent of x. Got this written down in my notes. Okay? So we're approaching 0 from the positive side. The reason we have to do 0 from the positive side is cotangent of x is the limit can't be defined as just the limit as x goes to 0 because it approaches 2 different infinities. So let's plug and chug and see what we get. So plug it in, plug it in. I plug 0 in, this goes to 0. So I got a 1. The cotangent, if you think about what cotangent looks like, I know that cotangent goes at 0. I know that it goes to what? Positive infinity, right? So this is going to be 1 to the infinity. Frowny face. Now I'm going to do a trick here, okay? And some of you may like this trick and some of you may not. But whether or not you like it or not doesn't really matter because it's going to be really, really helpful, all right? And I'm going to walk you through all the steps and you're going to do what I do. Otherwise, your life is going to get a little bit crazy when you try and deal with these kinds of limits. So you want to be really systematic because there's going to be a lot of steps. All right, so watch what I do here. I know that I need to turn this into one of these, or I can't, well, that was weird, or I can't do anything. So watch what I do. I also know that e to the natural log of anything is that anything. True? So I'm going to rewrite this so that it looks like this. The limit as x approaches, 0 from the positive side is equal to e to the natural log of 1 plus sine of 4x raised to the cotangent x. Now, why did I do that? Well, the reason that I did that is because anytime I see one of these three indeterminate forms, what I really want is to get it to this form. I want to get it to 0 times infinity. Because if I get it to 0 times infinity, then I can turn it into one of these guys, which is where I need to be to use L'Hopital's. So my biggest problem here is that I have this exponent. I need to lose the exponent. So the trick is to take the natural log of this term so that I can stick the exponent out in front as a coefficient. But I can't just take the natural log because that completely changes the limit. So what I do is I take e to the natural log of the thingy-dingy. Now, there's something that's really important to remember about limits. Because I'm composing two continuous functions, especially as x approaches 0 from the positive side, if you recall, I can stuff this limit inside. So in other words, this limit can jump up in and just deal with this function, because e is just a constant, right? I'm just taking e and I'm raising it. In other words, the real action is taking place in the exponent. So I don't really care about e just stays the same. The limit I'm going to stick up in here. So this becomes e to the limit as x approaches 0 from the positive side of the natural log of 1 plus sine of 4x raised to the cotangent of x. Now, this e is just going to be along for the ride for the entire problem. We almost get to dismiss it, but we can't because it's always there. Okay? Now watch what happens. Excuse me. This becomes e to the limit as x approaches 0 from the positive side of cotangent of x times the natural log of 1 plus sine of 4x. Whoops, natural log of, I put my parenthesis in the wrong spot, didn't I? Of 1 plus sine 4x. Now, this is where all the action's taking place, right here, up here. All right, remember, e is just along for the ride. So when I plug 0 from the positive direction in, watch what I get. I know that this goes to infinity. I know that this, if I plug it in, I get sine of 0 is 0. 1 plus 0 is 1. Natural log of, there we go. Sweet. Now I'm in good shape. Let me change back to my blue, and let's see what happens. Now I get e to the. Now here's the hard part. What do I want to do? Positive. Whoops, 0 from the positive. There we go. Ugh, that's awful, but you know what I'm doing. Do I want to rewrite this? There's two ways that I can rewrite this. Let's put them in red, not that you would be in trouble. I can either write this as cotangent of x over 1 over the natural log of 1 plus sine of 4x. This would be infinity over infinity. That would give me this. Here's the problem. I know that I'm going to, by L'Hopital's, I'm going to take the derivative of this. That's not too bad, right? That's negative cosecant squared. I know I'm going to have to take the derivative of this, and this looks awful, right? Because I'm going to have negative 1 over this squared times 1 over this times, right? It looks more onerous than it needs to be. So let's look at the other one. Let's look at the natural log of 1 plus sine. By the other one, I mean the other method. I can do this, and then I can do this. Now you may say, Ripley, wait a sec, 1 over cotangent x, why is that any easier? Well, let's look close. Isn't 1 over cotangent x equal to tangent x? And then when I plug 0 in, I get 0 over 0, and it's much prettier. Oh, I think we should probably use this method. Always looking for the path of least resistance. Always. Sometimes you just got to put your head down and plow through the work and it's going to be awful. But oftentimes it cleans up into something way prettier. So let's see what happens. Heck, I may be wrong. I may be dead wrong. But it's worth trying because it's a heck of a lot easier taking those derivatives of this new ratio that produces the 0 over 0 than it is to take these derivatives of this relationship that produces the infinity over infinity. Now, don't default to the one that always produces 0 over 0. Sometimes, depending on the function and the behavior, it might be easier to go this route. All right, so let's see what happens. This becomes the natural log of 1 plus sine of 4x over 1 over cotangent x, which we know is tangent x. Now, if I plug x equals 0, if I plug 0 in, what do I get? I get 0 over 0. Smiley face. So here's where notation becomes really important. By L'Hopital's, E is along for the ride. Limit as x approaches 0 from the positive side. Derivative of the top, slow down. We've got ourselves a chunk of chain rule to deal with, okay? So here we go. 1 over 1 plus sine of 4x. The derivative of natural log of blah is 1 over blah times d blah. The derivative of 1 plus sine of 4x. Now I've got another chain rule, don't I? Because I've got sine of blah. So this is going, the 1 disappears, derivative of 1 is 0. So this becomes cosine of 4x times 4. Chain rule, notice I had natural log, sine, and 4x. That's 3 functions. That's 3 derivatives by chain rule. And then I'm going to divide the whole thing by the derivative of tangent x. Remember, we're not using quotient rule. All right, we're just taking the derivative of the top, pow, and the derivative of the bottom, booyah. And here I go. Now let's see what happens. Plug x equals 0 in. If I plug x equals 0 in, I get 1 over 1 plus sine of 0. Ooh, that turns into a 1. That's cool. The cosine of 0 is 1. Oh, sweet. Look at this. And then I've got myself a 4. I know that the secant of 0 is 1. Yay, because it's 1 over cosine, right? And 1 squared is 1. Hey, guess what? This whole thing, this guy right here, I'll do this parenthetically, turns into a 4, which implies the entire limit turns into an e to the 4th. Look at that. E to the 4th, which is, I mean, it's pretty close to 3 to the 4th, right? Which is a little less than 81. Which means back here we had a 1 to the infinity. So we met somewhere between 1 and infinity, which happens to be e to the 4th. Okay, that's it, you guys. This is a beefy section. But L'Hopital's is so clever, and it's going to make you think about limits in a different way. It's also a wonderful tool for proving things like the limit as x approaches 0 of sine x over x, right? That's a heck of a lot easier than trying to do it numerically or algebraically. I can just go, pow, L'Hopital's, bam, 1, done, which is awesome. Okay, enough of me yapping at you. Hope you enjoyed. See you in the next lesson.